computer organization and architecture. Next, our syllabus. According to our style, the subject given by the gate pattern is divided into 7 units. First one, computer arithmetic. Very important topic. Definitely we expect one question from this. Next, memory organization. It is most important topic. Most important topic it is. Next, secondary memory, basic processor organization, pipeline organization, control unit design, I/O organization. Here, I am going to explain the weightage of our COA subject according to the chapters, year-wise. Watch this. In previous regular class also we discussed the same. First one, computer arithmetic. 2016, S1, S2, means set 1, set 2 like that. In 2024 also, set 1 there is one question, set 2 also there is one question. Next, memory organization. It is the weightage sheet. Watch all these things clearly. So, in 2024, if you watch 2024, 7 questions were there from our subject in both set 1 and set 2. It is the importance and energy of the subject. At the same time, if you watch the 2020, 9 questions, 2018, 7 questions, 2021 set 2, 6 questions, 2023, 6 questions, 22, 7 questions. It is the importance. And 2017, set 1, 8 questions. Okay, it is the importance of our subject. Let us start the subject. First one, computer arithmetic. This topic is very closely connected to the number system in digital subject. If you don't know the basics of number system, especially shortcuts in number system, it takes longer time to solve the problems from computer arithmetic. That's why I am going to explain only shortcuts here. First, different multiplication techniques. Before this, watch this. Here, how to make conversion? Unsigned decimal to binary, signed decimal to binary. If it is unsigned, given data is in decimal. Let the given data is, suppose 25. It is decimal. It is in decimal. Not needed to write base, just it is in decimal. If base is not there means in default it belongs to decimal. What is the binary value for the same? Here, according to textbook style, you have to divide the same thing with the target system base. 12's remainder 1, 6 remainder 0, 3's remainder 0, 2 1's remainder 1. So, finally, what about our answer? Our answer is nothing but 1 1 0 0 1. If you have any doubt in our answer, here 1 2 4 8 16 self check is there, nothing but 25. It is the longest method. What is the shortest method? Without performing division operation, shortest method is like this. 25. Its closest value in base 2 order. Nothing but its closest value in base 2 order, smaller value, not longer value. 16. So to produce 25, we require 16. What about next value right side to this bit? Half means 8. 16 plus 8, 24. 4 is not needed. 2 is not needed, 1 is enough. So, if you know this shortcut, it saves our valuable time. Suppose, if it is 520, what is the binary value? Now, we are discussing the unsigned value. 520 means, watch this. It is the unsigned decimal value 520. What is the closest value in base 2 order? Nothing but 512. To write 520, we require 512. What about next value? 256, not required. 128 not required, next 64 not required, next 32 not required, 16 not required, 8 is required, 4, 2, 1 are not required. If you have any doubt in this answer, our shortcut is there. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. Value is nothing but 520. Okay. When it is given in signed format, question is given and it is mentioned as signed. Type of representation is not given. Signed data can be expressed in 3 formats. Signed magnitude notation, signed 1's complement notation, and signed 2's complement notation. Here, when the type of representation is not mentioned, nothing but signed 2's complement notation for this. Suppose, if it is minus 25, same. What is the binary value for the same? There are 2 methods. In first method, separate the sign bit, means S is equal to 1. To represent negative data, sign bit is 1, and find the binary value for 25, perform the 2's complement for the same, because negative value cannot be produced in the normal format, it is produced in the 2's complement only. But according to our shortcut, minus 25, we require minus 32. To write minus 25, we require minus 32. Minus 32 balance is plus 7. What about next value? 16 not needed, 8 not needed, 4, 2, 1 are needed. Means, while writing the decimal value for the given signed data, when the data is expressed in 2's complement notation, same procedure. 1, 2, 4, 8, 16. MSB weight sign is negative. Suppose, when the given data is like this. If it is unsigned, what about decimal value? Now it is in binary. What about the decimal value? If it is unsigned, decimal value is like this: 1, 2, 4, 8, 16, 32, 64, 128. If it is unsigned, 128 plus 2, 128, 1 minute. Look here, now it is in binary. If it is unsigned value, then decimal value is like this: 1, 2, 4, 8, 16, 32, 64, 128, 256. Then what about our answer? 256 plus 1, 257. If the data is expressed in signed 2's complement notation, then its value is only MSB weight sign is negative, that's why minus 255. It is the procedure, it is the shortcut. Okay? Next, different multiplication techniques. Already we know how to perform multiplication in a system. Means in processor internally, what are the different steps used to perform multiplication? First one, repetitive addition. What does it mean? Given data can be added for number of times. 3 into 5 is there. 3 can be added for 5 times, or 5 can be added for 3 times. It is known as repetitive addition. What about second one? Shift and add technique. In this, shift left is used to perform multiplication. Shift right is used to perform division. Third one, Booth's algorithm. First of all, look here. First one, repetitive addition. Second one, shift and add technique. Third one, Booth's algorithm. here first one repetitive addition, second one shift and add technique, third one Booth's algorithm. In shift and add technique, what happens? Look here. Suppose given data is like this, minus 32 into 8. Here it is known as multiplicand. M represents multiplicand, Q represents multiplier, M into Q. It can be written as minus 32 into 2 power 3. Why we are writing Q value in base 2 order? Because we are discussing binary multiplication, binary system basis 2 in this minus 32. Here, already we know minus 32, how to write the binary value in sin to 2's complement notation. Minus 32, 16, 8, 4, 2, 1 into 2 power 3. Now we have to shift the data to left. For how many times? 3 times. That's why result is nothing but 1, 5 zeros. Again, 3 zeros. Why? While shifting the data to left, zeros are added at right side. How many zeros? Number of zeros to be added at right side is equal to the exponent value, 3. That's why. What about our result here? Our result is nothing but minus 256 minus 32 into 8 minus 256. What about result generated by the system in this manner? Same, 1, 2, 4, 8, 16, 32, 64, 128. What it is? 256. MSB sign is negative. MSB weight sign is negative. That's why its value is minus 256. At the same time, here only shifting is enough. Addition is not required. Suppose if given question is like this. Minus 9 into 9. What about decimal value here? Minus 81. In this, minus 9 means already we know. Minus 16, already we know how to write the value in binary directly. Minus 16, 8, 4, 2, 1 means plus 7, minus 16, minus 9 into 2 power 3 plus 1. Now, for this, perform shifting and for this, perform addition. Here, its value simply 1, 0, 1, 1, 1 into 2 power 3 means add 3 zeros at right side plus again same value 1, 0, 1, 1. Add this one, but while performing addition operation on signed data, both data must be same. That's why pad the sign bit to left. Why? To equalize the data. That's why. Now look here. 1, 1, 1, 1, 0, 1, 0, 1, 1. In this, in nothing but a dummy bit or guard bit. What about our value here? Minus 81 means 1, 2, 4, 8, 16, 32, 64, minus 128. So what about our answer? Minus 128 plus 32 means minus 96. Minus 96 plus 15 means minus 81. Okay. Next, what about Booth's algorithm? Third one, Booth's algorithm. In this, first you generate the Booth's code. How to generate the Booth's code? Suppose Booth's multiplier is like this. Multiplier means Booth's multiplier. Suppose if it is minus 18. First, find the binary value for the same. Now in this, minus 32, minus 18 can be written as minus 32, plus 14, minus 32, 16 is not needed. Next, 8, minus 32 plus 14 means 8, 4, 2, 1. If you have any doubt in this, 1, 2, 4, 8, 16 minus 32, answer is nothing but minus 18. Okay? In this, first write the binary value for the multiplier. 1, 0, 1, 1, 1, 0. Take one special bit at right side. Always that special bit is 0. Now, scan the successive bits. While moving the scan, when scanning moves from 0 to 0, no operation. Right side 0, left side 1. The shifted multiplicand is added for minus 1 times. Both are same, no operation. Both are same, no operation. 1 to 0 means right side 1, left side 0. Plus 1 means the shifted multiplicand is added for plus 1 times. Here, minus 1. So what about the code for this? Booth's code. Code means Booth's code is nothing but minus 1, plus 1, 0, 0, minus 1, 0. In this, look here, 1, 2, 4, 8, 16, 32. I am going to self-check whether our answer is correct or not. Minus 32 plus 16 means minus 16, minus 2, minus 18. It is the procedure how to check our Booth's code for the given multiplier. Okay? Next, floating point representation. Floating point representation is used to provide more range when compared to the integer representation or fixed point representation. To represent a data, to represent the given data in floating point notation, the following parameters are needed. What those are? Look here. We require exponent. First of all, base. Base is also known as a radix. Base is also known as radix. Next, exponent. Sign of the exponent. Sign of the exponent and with the respective system base. Here, exponent sign can be positive or negative. Binary system base is nothing but 2. When the question is given like this, data is given, base is not given, default, it belongs to binary only. That's why I have to take 2 in the place of base. Now, in this, to represent floating point data, to represent the data in a floating point representation, to represent the data in floating point notation, in this we require system base. In default, it is nothing but 2. Exponent, mantissa, sign of the exponent, sign of the mantissa. Only sign of the mantissa tells the sign of the data. So, to store that one in a register, what is the need to store the value in a register? If you want to apply the same to a system, first you store that value in the register because processor can read the information when it is available in register only. That's why the standard procedure or standard format to represent floating point data is nothing but first S. What S tells? Sign of the mantissa. MSB is allocated to represent sign of the mantissa. Next, middle field, capital E. What is capital E? Biased exponent. Next, what is last one? Mantissa. Now in this, we are discussing standard representation. Representation sometimes known as notation. what S tells? S tells the sign of the mantissa, and capital E, biased exponent. Biased exponent means it is unsigned. What is the difference between small e and capital E in our style? Small e, true exponent. What capital E tells? Biased exponent. Biased exponent means it is signed. It is signed. Sorry. Biased exponent means it is unsigned. True exponent means it is signed. Once again, small e represents a true exponent. Capital E represents biased exponent. Biased exponent means it is unsigned. What is the expression to find the capital E here? Small e plus b. What is b here? Amount to be biased. Amount to be biased. In this, middle field is used to represent biased exponent, means it is unsigned exponent. When exponent is expressed in unsigned, no sign symbol is needed. And M means mantissa. Mantissa is nothing but, generally mantissa is represented in the signed magnitude notation for easy conversion. Easiness of the conversion, that's all. It is the standard procedure. Okay. What is the amount to be biased here? Let the size of the, generally, let the size of the exponent field is k bits. Generally, biasing value is nothing but 2 power k minus 1. 2 power k minus 1. K minus 1 occupies in exponent field. Okay. Next. What is normalization? Look here, normalization. What is normalization? It is the process of maintaining the non-zero digit in the MSB of the mantissa. Here, let the mantissa is like this. Let it is mantissa. It is a non-normalized mantissa. Non-normalized. What is the meaning of that? Normalization is not done for this. If it is normalized, this bit must be 1. Now, let the mantissa is like this. Whatever the size of the mantissa doesn't matter. It is nothing but mantissa. MSB is 1, that's why it is nothing but normalized mantissa. M means mantissa. Okay. Next, normalization can be done in 2 ways. What is first one? Explicit normalization. Second one, implicit normalization. Here, if it is explicit normalization, compulsory MSB of the mantissa. What is MSB of the mantissa? Next bit to the, next right side bit to the decimal point. Compulsory it is 1, remaining, what about remaining all bits? Doesn't matter. Now it is explicit normalized mantissa. If it is implicit normalized mantissa, to perform implicit normalization, first to perform explicit normalization, later have to shift the data to left. Means, have to shift the data to left means 1 point. Whatever the remaining bits doesn't matter. In this, generally it is represented, it is used to represent mantissa. What is the name used to represent this? Hidden bit. Where it is hidden? In the place of integer. So, hidden bit is not needed for explicit normalization. In this, no hidden bit. Hidden bit is needed only for implicit normalization. IEEE standards use only implicit normalization. At the same time, what about expression values? Expression value means how to find the decimal value for the given expression. If it is explicit normalized technique or implicit normalized technique. Look here. If it is explicit, what about the expression value? No hidden bit is there. That's why -1 whole power s. What is s here? Sign of the mantissa. If it is 0, it becomes positive. 1 becomes negative into 0.m into generally basis 2 here, system basis 2 capital E minus biasing value. What B tells? Amount to be biased. Next, if it is implicit normalization, here all things are same, -1 whole power s into not 0.m, 1.m into 2 power capital E minus B. No hidden bit is needed for explicit normalization. That's why we take 0.m. Hidden bit is needed for implicit normalization. That's why we write 1.m. In this question is given. Type of normalization is not given. You should follow only explicit normalization. But in that question, if we mentioned IEEE standards use only implicit normalization. Here, IEEE standards use implicit normalization only. Next, IEEE standards used for floating point data representation. Here, there are two sizes to represent data. In IEEE standards. Which data it is? Floating point data. Here, already we discussed, to represent floating point data, we require mantissa, sign of the mantissa, exponent, sign of the exponent with the respective base. Here, respective base here, it is nothing but base 2. Exponent sign can be positive or negative. Mantissa sign can be positive or negative, but only mantissa sign tells the sign of the data. Exponent sign represents the location of the decimal point, means where decimal point is located. That's why in a register, while representing the floating point data in a register, MSB is allocated for representing sign of the mantissa and no bit is allocated for representing sign of the exponent. Why? Signed exponent is going to convert into unsigned exponent. That unsigned exponent is technically known as biased exponent. In our style, capital E is used to represent biased exponent. Already I explained capital E, nothing but small e plus b. Capital E, biased exponent, unsigned, signed exponent, amount to be biased. In this, there are two methods to represent floating point data in IEEE standards. First one, single precision. Second one, double precision. What is single precision and what is double precision? Single precision size is 32 bits. Entire register size is 32 bit. Double precision size is 64 bit. Entire register size is 64 bit. Okay, come to first one, single precision. Definitely we expect one question from this. from double precision, earlier we don't have the questions, but single precision, 99.99% chance is there to get question from single precision. What is the size of the single precision? 32-bit. Single precision notation. Notation is also known as representation. Notation is also known as representation. In this, you must remember one point here. What it is? Expression value -1 whole power s into 1.m into 2 power capital E value minus 127. Why? Amount to be biased is nothing but 127. Why? In IEEE standards, biasing value is nothing but, what is the amount to be biased? 2 power k minus 1. In general notations, in IEEE notations, 2 power k minus 1 whole minus 1. And IEEE standards are used to represent not only number, special values, plus or minus 0, plus or minus infinitive, not a number. We are going to discuss those also. Now, biasing value is nothing but 127. It is your responsibility to remember this in single precision. Okay. At the same time, what about the register? Components used in the register. Let it is the register. Register size is 32-bit. In these 32 bits, MSB is allocated for sign of the mantissa. Next, 8 bits are allocated for biased exponent, and mantissa size is 23 bits. And mantissa is expressed in signed magnitude form only. Remember this. Mantissa is expressed in signed magnitude form only. Here, size of the E field is 8-bit. That's why apply 8 in place of k. What k tells? Size of the exponent field. That's why 2 power 7 minus 1. 2 power 7 means 128 minus 1, 127. It is your responsibility to remember this. Okay. Next. Already we discussed what is the sign of S here, 1 bit, sign of E here, 8 bit, sign of M here, 23 bit, size of S 1 bit, size of E 8 bit, size of M 23 bit, total 32 bit. In this, these points are very, very, very important, be dedicated here. Zero or 1, yes, S value can be 0 or 1. E0 means all 8 bits are represented with 0. M is also 0. Mantissa is also represented with 0. Nothing but plus or minus 0. It is not normalized 0. Special value 0. Special value plus or minus 0. Now, when it is said to be plus 0, S0 plus 0, S1 minus 0. Okay, now, for this, earlier one question was given like this. Question was like this, 0x watch question carefully. This data is in IEEE single precision notation. Zero x means this data belongs to hexadecimal. 8 7 zeros. He is in IEEE single precision notation. Its value is, it is MCQ question, options are like this. normalized plus 0. Next, normalized minus 0. Next, special value plus 0. Next, special value minus 0. Let the given question is like this. How to solve this one? What is the procedure to get solution in easiest method? Here, given data is in hexadecimal because 0x, if we write 0x before data, that data belongs to hexadecimal. That's why if you make conversion into binary, 8 means 1000, remaining all are zeros. Already we know the format. MSB tells sign. Remaining all are zeros means mantis are 0, exponent 0. So it is not normalized 0. Special value 0 cannot be normalized. That's why option A and B are false. Why? 0 cannot be normalized. It is nothing but special value. That's why special value plus 0, special value minus 0 means correct answer is special value minus 0. Why? MSB is equal to 1. It is the procedure how to solve the question at shortest time. You should apply the technique properly. Next, here 0 or 1. Here E value is equal to 0. Here E value is equal to maximum. Now here E value is minimum. Here E value is maximum. E means here capital E means biased exponent. Capital E value minimum and maximum are allocated for representing special values. Now E value is equal to 255 means 8 ones. 255 decimal means 8 are ones. M is equal to 0, same. Means plus or minus infinitive. It is also special value. It is also special value. Next, 0 or 1. S value can be 0 or 1. Next, E value maximum 255. And M value not equal to 0. You have to understand the difference between second and third one. Then it is not a number. What is not a number? Square root minus 1, something by 0. Now it is also special value. So what about final conclusion from this? Capital E value minimum and maximum are allocated for representing special values. Next, to represent implicit normalized number. Implicit normalized number. Number or value. What about the values of capital E and M? It can be 0 or 1. In this, E value can be greater than or equal to 1, less than or equal to 254. Why? E value 0 and 255 are, E value 0 and 255 are allocated for representing special values. That's why to represent implicit normalized number. What about these? Capital E range 1 and 254. What about M value? Any? It is nothing but okay. Next, another case is also there. That was given in 2021 GATE. It is your responsibility to understand this one. Last point, very, very, very important and powerful point. 0 or 1. Look here. S can be 0 or 1. E value 0 means 8 are 0. Here m value 0, then special value plus or minus 0. Here m value is non-zero, except 0, any other value, but what is capital E value? 0. What it represents? What it represents? It is your responsibility to remember. Nothing but d-normal number, d-normal or denormalized number. Normalization is not possible to perform this. In 2021, one question was given based on this one only. It is your responsibility to remember, because compared to remaining all points, it is very, very, very important. Okay, next. Watch these points once again clearly. Next. How to solve the question in short test method. Look here. Store 26. Base is not given means in default it belongs to decimal. In IEEE single pressure notation, IEEE single pressure notation, and express the value in hexadecimal notation. Already we know, while representing hexadecimal data, each hexadecimal digit requires 4 bit directly. Multiplication and division operations are not needed to make conversion between binary and hexadecimal and binary and octal. Each octal digit is represented with 3 bit directly. Each hexadecimal digit is directly represented with 4 bit. Here, watch the question carefully. Store 26 in IEEE single pressure notation and express the value in hexadecimal. Here, sign symbol is not given, means automatically S is equal to 0 default, because sign is nothing but positive. 26, it is decimal. Find the binary value. 16, 8, 16, 8, 24. 4 is not needed. 2 is needed. 1 is not needed. So 1, 2, 4, 8, 16. 16 plus 8, 24, plus 2, 26. Now in this, it can be written as into 2 power 0. Convert the same thing into floating point notation. Since it permits, since IEEE standards permit implicit normalization, it can be written as 1.1010 into 2 power. While shifting decimal point to left, what happens? Exponent is incremented for how many times? How many number of times we have shifted the decimal point to left? 4, that's why 4. Already we know name of this bit, hidden bit. Hidden bit means no space is needed in the register. Next, what is the name of this? Mantissa. Next, what about this one? Exponent means true exponent. It is nothing but 4. Already we know biasing value 127. That's why what about capital E here? 127 plus 4, 131. Is it signed or unsigned? Unsigned. So what about binary value here? 131 means 128. 64, 32, 16, 8, 4, 2, 1. Okay, size of E field is 8-bit. Now store the values in the 32-bit register in this. Look here, S, E, M. What is S value here? Nothing but S is 0. What is capital E here? Capital E is nothing but binary value for 131 means 1, 5 zeros, 1, 1. What is M value here? It is nothing but 1, 0, 1, 0. Remaining all are zeros up to 23 bits. Total size is 32-bit. Why? In IEEE single precision, total register size is 32-bit. Now, convert the same thing into hexadecimal. Means here we require 4-bit string. Remaining all are zeros. 0, 1, 0, 0 means 4. 4. 0, 0, 0, 1 means 1. 1, 1, 0, 1 means 13 means D. Remaining all are zeros with base 16. So it is our answer. If you have any doubt in this answer, self-check is there, and that self-check is used to know how to find the decimal value for the given IEEE standard value.